Yeah. So last time, we discussed about this correlation coefficient, and also what was the other thing? The coefficient of determination, like this one, and it had a particular name or the notation. Oops. Of R squared, right? So this is an official name of this measure. After you fit the linear regression, and then compute the sum of residual. Okay, so the sum of residual, let's see. Sum of squares over residual, which is simply is yi minus a minus bxi squared, and then their sum, right? So after fitting this linear regression model, and then we compute this error, right? And then take the square of it and then sum them up, and then that's called this SSR, right? And then let's see. So we proved that. Did we prove or not? But we studied that this SYY, which is the variance of y, is always greater than this value or equal to this value, right? And then we understood it from this measure, right? Yep. And then we just take the difference between them. So this was an error even after fitting the linear regression model, and then this one is the total variance that y has, and then the difference is the amount of fitted value, right? So the amount of an explained part or explained portion from y, the total variance of y, and then we divide it by SYY, which is the total amount, and then it's it is always between 0 and 1, right? And then 1 means it has no error, which is this where this SSR is 0, and in this case all the data points are exactly along the single line, right, with no error, right? And in this case, we can view it as a perfect fitting of the given data by using this linear regression line. Okay, and then 0 means we can we failed to fit any of the data given data of y. Yep. So in this case, so we have a 0 value of this coefficient of determination, and then after some proof, we show that this R, this R is a correlation coefficient that we studied, that we learned previously, and then take the square of it, and then it is actually the same as our R square, or this the relative fitted value. Okay, and so the only difference is this R. R squared is also 0 to 1, but the original R, which is this one, is ranging from -1 to 1, right? So we can have of course, negative correlation, and in this negative correlation case, and then the slope, the fitted slope in our linear regression model is having the negative slope, right? So in this case, even though we do not prove it, but this B will be negative value, which is our linear regression line has a negative slope. But even though R is ranging between -1 to 1, after taking the square of it, and then it will be between 0 and 1. Okay, so that was the review of what we learned last time. And then the next part is about this analysis of a variance. Analysis of residuals. So this is a quite practically useful technique or useful thing to know. Okay, and so this SSR, yeah, SSR, yeah, which is the, yeah, YI, yeah, so this guy is squared and sum of them, right? So this is a SSR, and then if we divide it by sigma squared, which is the variance of the original error term, which is this guy, and then this guy is following the chi-square distribution, and then we have yeah, two parameters that are kind of biased towards our data, and so due to those two parameters, we have a, yeah, like a less freedom, less degree of freedom. So in this case, we learned that this guy is following the chi-square distribution with the degree of freedom of n-2, right? Okay, and then from here, yeah, from here, let's think about the estimate of the variance, or estimate of this sigma squared. So, yeah, as I mentioned, this measure is the chi-square distribution, right? And then what is the mean of this one? What is the mean? So let's consider the mean of this value. So again, this part, yeah, so let me rewrite it here. Right? And then let's think about its expectation. So what is the expectation of it? So it is, in other words, what is the mean of this chi-square distribution with the degree of freedom of n-2? n-2, right? What was the variance then? Variance was 2 times n-2, right? Okay, yeah. Okay, and then yeah, we have the expectation of this one, and then yeah, we do a little bit of a trick to obtain this estimator, and then yeah, what about this guy? So this is a constant value, although this is an unknown parameter, but this is a constant value, but not a random variable. And then yeah. So this one, okay, and then what is the expectation of this guy? Okay, then again, then let's take this the step by step, and then what is the expectation of this? Expectation of this is this times this, right? Because that is a constant, and then yeah, as we can see, this guy can also be moved inside of this expectation, right? And so this is the result. And then what is the expectation? Sigma squared, right? And then from here, what we utilize is we compute this statistic, okay? And then we just use it as an estimator for the sigma squared. Okay? So if we use this guy as an estimator for sigma squared, and then it is at least what, unbiased estimator, because this estimator's expectation value is the same as the true parameter value. Okay, so we will use this trick in the next chapter. I mean, yeah, maybe in 10 minutes. Okay, and then this guy had the notation of SSR, and then n-2, right? So it is just a rewritten by using this SSR as a the notation that we use, and then this guy is an estimator again for sigma squared. Okay, and then what about this standard deviation? and then we can just take the square root of it, and then the estimator of the standard deviation can be viewed as this, right? And so, yeah, so let's compare this guy with this. II minus alpha plus beta xi, and then sigma. So what does it follow? Or more simply, what does the numerator follow? So what is it? It is epsilon I is following Gaussian distribution with the zero mean and standard deviation of sigma squared, right? So that was the starting point, right? That is our initial assumption that we started with. And then, okay, and then the numerator is just nothing but epsilon I. And then we just scaled by its own, sigma value or standard deviation. And then this one will exactly follow this guy, right? No. Yeah, this one will exactly follow normal distribution with the zero mean and the unit variance or the variance of 1, right? Okay, and then let's compare this guy with this, and then we just change it alpha and beta with our estimation value, and then the sigma or the true standard deviation value as this estimator that we obtained here. Right? Okay, and then what will this follow? This will kind of follow some T distribution, right? So T distribution, but we do not, in this particular task of this analysis of variance, residuals, and then let's just assume it, although it is wrong, but let's just assume it as just a standard Gaussian random variable. So T and Z, or standard Gaussian, and T distribution has some relationship where this n gets infinity, and then the distribution will converge to this standard Gaussian distribution, right? So what was the definition of Z? The T, it is Z over chi-square distribution, with the degree of freedom n divided by n, right? So it can be viewed as the estimator of this unit variance of that, it will approximately give 1, right? Because the chi-square distribution is the sum of a squared random variable, right? So we are just reviewing them, and if n was like 3, and then it will be just like z1 squared, z2 squared, z3 squared. And of course, these z's are independent and different from this z, right? So numerator and the denominator should be independent, but we do not know. We didn't prove rigorously, but in many cases, or this guy and this guy were independent, right? So that satisfied the requirement of the T distribution. But anyways, this guy, we know that this guy has the mean value as 3, right? Because each one will have the expectation value as 1, right? And so the total expectation is n, or 3 in this case, and then divided by 3 in this case, and then it will approximately give 1. So you can think of it as some kind of an approximate version, or a little bit of inaccurate value of 1, which represents the variance of standard Gaussian. Okay, the standard Gaussian will have the variance as 1, but we are using some approximate value or some estimator for the variance of the standard Gaussian. Okay, so this is the meaning of the t distribution. So yeah, it has almost the same meaning. So we had a sigma here, and then sigma will be also used in the denominator, and then yeah, so that will kind of be converted into this kind of form, and so it would be following z distribution, the t distribution. But yeah, in this case, by definition of the t distribution, if n gets large, and then this one will be really close to 1, which means if we view this part as the estimator of this true parameter 1, which is a variance of standard Gaussian, and then if n gets large, and then the variance of this part, so this one will be really close to 1, maybe 1.001 and something like that. Okay, but if n is relatively small, and then it will have maybe 1.3 or so, right? So it will have a larger error, right? So n gets infinity, and then this one will be really close to 1, and thus it will be converging to just a z. Okay, so back to this. So even though this one follows t with the degree of freedom of what? n minus 2, right? But let's just view it as z. Okay, just the standard deviation, or I mean the standard Gaussian. Okay, and then this guy, again, since it is a standard Gaussian, this one is approximately having the mean of 0 and variance as 1. Okay, and then let's look at the figure first. Suppose your data is something like this, and then suppose after, given this data, you have, you obtained this fitted line or this linear regression line, and then what is the residual? Sum of squares of a residual, which means, like this case. So this guy is an individual error at the data point I, right? And so this guy in this graph will be corresponding to this kind of an error, right? Right? And then let's just plot these errors. I mean, let's just take these errors out and then redraw these errors only. And then this is the figure that we get. Although it looks much larger, but if you see the scales of y-axis, and then it is much larger, right? Okay, and so this error, this first error of the first data item is actually this guy, right? And then the second one is drawn as this line, right? So you know how to draw this guy, right? Okay, and then what should this point or this measure should follow? So this one was 1, and this one was minus or negative 1.5, and this one was really close to 0, so 0.03, for example. And this guy is maybe 0.9. Okay, so these values are actually this guy, which should follow a z. Okay. Okay, and then in this really lengthy slide, the main message is this. So if it really followed this standard Gaussian distribution, then let's think about this guy. The probability of this, so this z ranging from minus 1.96 to 1.96, roughly like negative 2 to positive 2. Okay, so in this case, the probability should be 95%. And so if we had a maybe 100 point, or 100 points were initially given in order to fit our linear regression line, and then after computing, after fitting their linear regression line and then compute the residuals for each data point. And then if we draw them in this manner, and then, okay, I'll choose pink. So ranging between -2 and 2, okay? In this range, there will be approximately 95% of the residuals out of 100 residual values, right? Yeah. Or you can maybe draw some histogram based on these measures. So we just bring these values: 1, minus -1.5, -0.3, 0.9, yeah, 0.09, and so on. And so we will have 100 errors, and then you can just draw some histograms, right? Some histogram, and then this histogram should approximately follow the standard normal distribution, or maybe more exactly, it should follow the t distribution shape, right? But they are kind of approximately similar or the same. Okay, but what if, okay, in this case it looks like yeah, it follows our kind of, yeah, some similar shape of a histogram or kind of a pattern to Gaussian distribution or standard Gaussian distribution. But what if our data was given in this form? So intuitively, we can see that their fitted line should be like quadratic line or hyperbolic kind of a shape, right? Not a linear shape. So in this case, let's see how these errors are shown. So we fit the linear regression line anyways, and then, yeah, it has this kind of weird shape, right? And also, yeah, this one is another kind of interesting case. So in this case, after fitting the linear regression line, the error seems to be quite small when x is small, but if x gets large, then the error seems to be increasing. So points gets more and more away from this fitted line as x increases. Okay, I mean, suppose some data have this kind of pattern. Okay, so in this case, yeah, even though it is not clear, but if we draw these residual, and then it will be something like this, but it will be really divergent, right? It can be kind of a plausible pattern that we may see. So in this case, it doesn't seem to, or it doesn't look like a Z or the standard Gaussian. Okay, and then what is the problem in this case? So what is wrong, or yeah, what kind of thing that we did wrongly? That yeah, did we do in a incorrect manner, or what is the problematic part? So the main problem that we see this kind of difference or kind of, yeah, unexpected behavior, which is different from our assumption that these errors should follow approximately some standard Gaussian. It means our initial assumption was completely wrong. What was our initial assumption? This y, yeah, will be exactly represented. Yeah, so if we know alpha and beta, I mean the true alpha and beta, and then some Gaussian noise, we should be able to construct this y values perfectly. I mean, assuming that we know alpha and beta, which means, yeah, this y is following this linear kind of, yeah, y has the linear kind of relations with the given independent variable x, right? But it actually turned out not to be the case. Okay, so in this case, yeah, in this like this curvature kind of shape, y is actually yeah, this kind of quadratic quadratic expression with maybe some error. Okay, in this case, this guy can be still modeled as this Gaussian, zero mean Gaussian random variable. Okay, but this was the true relationship, but we just wrongly assumed that y is represented as this, and so because we do not have this term, so this term is missing, and so epsilon is no longer following the normal distribution with the same sigma squared. Okay, with the same sigma squared. So that's why we see this kind of pattern. I mean, in some data, yeah, so linear regression is not a good choice because the data, I mean, the relation between x and y is not a linear. I mean, even after we know, even if we know the true parameter values, they are not a linear relationship at all from the beginning. Okay, so in this case, if we just apply the linear regression, it will be a little bit, it will be a little bit silly thing. Okay. What about the next case? In this case, does it look like a maybe hyperbolic kind of case, second order or third order? Yeah, what should we model them? Yeah, we can model them by using still a linear term, but it looks like the variance of an error or the amount of an error is increasing proportional to the x value. And then it means this error term, this error term is no longer following the Gaussian with the fixed variance. Actually, the variance is proportional to x value. So we can maybe model, we can change our model in this manner. Xi. Okay. So this one, after we use this one, and then it may kind of follow. It may perfectly fit our model or our data, given data. Okay, but from the beginning or in the starting point, we do not know whether this one is true or the default or the basic or standard linear regression one, which was following this guy, this default one. Yeah, we do not know whether this guy was true and that guy was true, or maybe that like a quadratic kind of a representation was true, right? So we do not know in advance. So what we typically do in this case is we just apply the linear regression and then look at these error plus and then see if these errors are looking like, or they look like following the Gaussian distribution with the fixed amount of variance. Okay. So that's how we verify our initial assumption that, okay, y is actually modeled as this. Okay, but if we do not see this expected pattern like this from our errors, and then we have to go back and then change our model, initial assumption. Okay, and then we may be able to try maybe this guy, and maybe this guy, and so on. Okay, and after fitting them, and then verify or visualize their errors, and then see if these errors are having the expectation, are showing the expectation pattern. Okay. So yeah, this kind of thing is really an important step. Okay. So yeah, so maybe in later years or when you join some company and then you are doing the job of analyzing the data, and then you just fit it or apply the linear regression model to a given data, and then your boss is asking that, okay, how do you make sure or how do you guarantee that your data is following this linear regression kind of a model? Okay, so what is the justification of applying this linear model? Okay, in that case, you should be prepared for giving an answer. I mean, proper answer for that. Okay, we started with this kind of assumption, and then we verified or analyzed these error patterns, and then it verifies our initial assumption of the linear relationship between x and y. Okay. So, oops, it's the same slide, and then so that's it for this chapter. And then there are a lot of stuffs in this chapter. Yeah, honestly, I didn't know which one to skip. Yeah, but yeah, I think at least if you have this basic ideas of what we went through, and then I believe it should be good at this point. And then this is a typo actually. So this is a not this one, and the skipped part is starting from 9.7. So from this 9.6 is actually this analysis of residuals. So this one is included in our exam and maybe in your homework. Yeah, and then after starting from this 9.7, we will just skip them. Yeah, so before ending this chapter 9, any questions? And the new homework will be probably announced maybe later today, I guess. So it will cover chapter 9, 8, and 9. Okay, and then let's move on to the new chapter, which is called this analysis of a variance, or it is called a ANOVA, which is this AN and O and VA. And this one will be our final chapter before ending the semester. Okay, and then let me give you like high-level story about what this ANOVA is doing. Okay, what is the problem setting that this ANOVA is taking care of or targeting? Okay, so the situation is, so since we are using a person's height and weight, and then let's just use this height example, although it's a little bit boring, but yeah. So let's just suppose we have a 40 people, and then we just split them randomly into 4 groups, like 10 of 10 each, okay, in each group. And then what we do is so in their early age we give maybe some milk or maybe Coke and juice maybe, and nothing, just water. Okay, and then what we want to find out is whether maybe milk or Coke or juice, those kind of different treatment. Okay, so different kind of independent variable that we vary among different groups. So does it influence the person's height in a statistically significant manner? So that is the question. Okay. So so among the so it's like, so when they were maybe at the age of 6, okay, so we keep giving this guy, and then we maybe wait for maybe 10 years, and then when they are 16 years old, and then we measure their height of 10 people in each group. Okay, so this is the story, and then suppose the average height of this 10 people after taking the milk for 10 years, and then it was like the average or the sample mean in this group was maybe 175, and then in the case of Coke 1 168, and maybe juice will be 172, and water, I don't know, maybe yeah, 176. Okay. So yeah, of course these numbers will be different. I mean, they will not be exactly the same, right? So they are just a sample mean from different sample, right? But can we be sure, or can we kind of claim that, or can we guarantee that, okay, because these values are different, milk will have some important influences on a person's height, or maybe Coke, yeah, we can do the same claim on Coke and juice and water and so on, right? So can we do this kind of claim based on this kind of sample mean kind of information? Or yeah, I mean, we do not just use this sample mean. Yeah, we have a full information of 10 people, for example, like 168, 175, 173, and 169. So suppose this one's average is 175. Oh, it doesn't look like it. 178. Okay. Yeah. Anyway, yeah. And so we had, yeah, so yeah, it's 4 people, but we have, yeah, suppose we have 10 people each, and then we have a full information about these observations in each sample. Okay. And then what can we do? Yeah, what can we do in this situation? And then we want to actually answer. Okay, so these are, the differences are, yeah, 7 centimeter. Is this a statistically significant difference? Different or not? So in this case, let's start with the initial assumption, or what is our initial starting point? Initial starting point is those samples are following the Gaussian, okay, Gaussian distribution. And then, yeah, so in terms of a hypothesis testing, we want to be able to claim, okay, we want to be able to claim that, so their means among different groups are actually different, okay? The true parameter of their means between different groups are different. So that is our alternative hypothesis that we want to claim. And then the other null hypothesis, or the default situation, is mu0, mu1, yeah, maybe mu1, mu2, mu3, and mu4, which is, yeah, each of which is corresponding to the true mean, right, of each group. So the default, or the null hypothesis, which is an uninteresting version, will correspond to this, okay? So in this case, let's suppose there are variances. So, so in this case, let's call that as just a single mu. And then suppose this guy, each of these observations are just following Gaussian distribution with maybe the true global mean value, or global, yeah, expectation value of mu, which is true parameter, and maybe maybe 5 squared, which is our variance. So the standard deviation of a person's height is 5, or the variance is 25. Okay, so this is the true parameter. Okay, let's just assume that. Okay, and then you guys can see that we have 10 numbers, or 10 observations, and then if we consider their sample mean, so this can be viewed as x1 bar. So this one is x2 bar. Okay, and then 4 of these sample means are just sample mean, right? And then what about their distribution? x1, 2, 3, 4. So each of them is actually following the same distribution. I mean, so we are considering again this situation where the mean are the same, and yeah, of course their variances are all the same for individual person's height. Yeah, in all of these groups. Okay, and then yeah, in that case, this sample mean, I mean, 4 of these different sample means will follow the same distribution with the same mean value. So yeah, let's just fix it as 1, maybe 70. So the true parameter was 170, and then the sample mean will also follow 170 as the mean, and then what is the standard deviation or the variance? We have a variance here, and then the variance will be what? Divided by what? So each of these x1, x2, x3, x4 is just a sample mean of 10 observations, right? And then individual one follow that Gaussian distribution with the variance over 5 squared, and then the sample means variance will be decreased, and the value will be 5 squared divided by what? 10, right? So this is just a property of our sample mean distribution, right? Okay, and then so in this case, so it generated differences of 7. Let's just focusing on the first group and the second group's sample mean. So the difference of 7 in this case, what will be the kind of a p-value? So when they are equal, and in this case, they have these two sample means. So the hypothesis is, so let's just remove these two other cases for now. And then between these two cases, the first hypothesis is these two are x1 and x2 bar, the sample means from these two groups are following the same distribution, more exactly, the same mean value. And the alternative hypothesis is these two values are different. And then, we start with the null hypothesis. Oops. Right, and then it will have a 170 and 25 over 10, maybe 2.5. So maybe something like this. And then, standard deviation is maybe 1.5. 1.5 squared is 2.25? Is it right? Or 2 like this? Which one is right? I got old, so I forgot it. Okay, so this is a standard deviation, right? Of 220, maybe 2.25. And then if we consider like 95 of a confidence interval, then it's like, something like this, right? And so, maybe, it is not an exact application. I mean, it's not in a correct way, perfectly correct way, but the value of 7 can be viewed as, so this one is maybe 4.5, and 7 is outside of this range, right? The mean difference, right? So more exactly, we studied about this case, right? So this is a two sample cases, whether the mean values are different or not, right? So we first consider this guy, x1 minus x2 sample means, right? And then if follow the, if mu1 and mu2 were the same, and then this guy will follow like a zero mean and some variance of a Gaussian noise, Gaussian random variable. But anyways, so this 7 is maybe outside of this class, and so we have to reject the null hypothesis, right? But as we can see, this value is really large, okay? And then even though we divide it by 10, this variant, this difference of 7 will fall into this region, right? Our acceptance region. So in this case, we shouldn't conclude that milk and Coke will have a statistically significant influences on a person's height, okay? But if 7 is shown to be really extreme value with a really small p-value, and then we have to accept the alternative hypothesis is by saying that, okay, so milk and coke will have some meaningful or non-trivial or statistically significant effect on our height. Okay, so this is an overview of what we will do in this chapter. And so as you can see here, the really important factor is this guy, the variance of maybe, we typically start with the distribution that individual observations are following, right? And so we all start from that value, 5 squared. But this value is not known, right? But anyways, we have to focus on that value, and so we kind of care, or we just spend a lot of pages, or you probably have to spend a lot of your time about how to estimate this value in this context of hypothesis testing, whether these whether these two or more groups will have a different means or not. So this is a big picture. So any questions so far? Okay, so let's read through our book. So, so this sigma squared. So we have to, let's see. So here, suppose we have one sample, or n observations within a single sample, right? And in this case, xi's are IID, or identically and independent and identically distributed, and then it follows Gaussian distribution with some mean and some variance. But here in this case, let's consider the situation that these are not actually IID in this case. So these are independent, but they are not identically distributed, but they have this Gaussian distribution. But I keep saying but the means are different. So the expectation values are different for each sample. So like this. So suppose we obtain the 3 observations, but the first observation was following the Gaussian distribution with the mean of maybe 3, and the second one is following maybe the mean of maybe 8 and maybe -5. But here our assumption is their variance are still common. Okay. We do not know why we should care about this case, but let's just follow this scenario. Okay, and then in this case, let's just transform each of our observations into some other number of zi, and as you can see, this guy will follow the standard Gaussian, because we just subtract its this value, its own mean from each individual observation, and then divide it by standard deviation, which is common value. Okay, then it's actually following the basically z, or 0,1 squared, right? And then given, suppose our sample x1, x2, x3 was actually maybe 4, 7, and maybe -2. So this one came from this distribution, and this one came from this, and this one came from this. And then, we just do this kind of conversion or transformation, and then for these converted value, we take the square of it and then sum them up, and then you guys will know this one will follow the chi-square distribution with the degree of freedom of n, right? So it is, it's just an obvious situation. Okay, and then let me do one thing. Let me do one thing. So yeah, let me just skip the scenario because it will be covered in the next slide in much more detail. So I think yeah, we can just go directly to here. So we now consider this situation. So in this case, we only had like 3 different samples having its own mean, but with the common variance. But what if we had maybe x11, x12, and x13, x14, which are indicating the first group. And so the first number is the group ID, and then the second number is observation ID, or the first number is the sample ID or sample index, and the second one is an observation index. Okay. So we now consider this situation, which is exactly like this situation, right? So in this case, the first number in the first group is x11, which is corresponding to first group and first observation within that. And then this guy is the third sample within the first group, and so it's x13. Okay, so you guys know this kind of notation, right? And then yeah, so in this case, we have, let's see, so we have 3 different groups, and each group has 4 numbers. And then, let's see, yeah, in this case, we have 3 different groups, right? 3 independent sample, or 3 different samples, and then each of sample will have the size of an n, which means each sample will have an observation of n observation, and in the previous case it was 4, right? Within each sample we have a 4 observation. Okay, so let's just be familiar with these notations, because they will appear in many times. And then as we assumed in the previous case, each group will have their own mean value, mu I. So yeah, this is just this situation. So like x11, so let me just clean it up. Then, so this guy is x11, x12, x13, x14 is all following this distribution. And then yeah, it is tedious, but the x21, x22, x24 is following this distribution. Okay, so this is the setting. And then let's call these different mean values as mu I, or mu1 and mu2 and mu3. Okay, so these are the 3 different mean values from each sample. Okay, and then let's just think about this case. So yeah. So x11 minus mu1 squared, and x12 minus mu1, because it had a true parameter of mu1. And then yeah, we skip 1 and this guy. Okay, and then divided by sigma squared. What does it follow? It's a chi-square distribution with the degree of freedom of 4, right? And then what about, we further continue adding x21 minus mu2 in this case, and yeah, and squared x24 minus mu2 squared, and then divided by sigma squared. So we have exactly 4 observations in the second group. So we assume that each group has the same number of data items, or same number of an observation. And the first group will give a chi-square distribution with the degree of freedom of 4, and then the second group will also give a 4 of degree of freedom of 4. And then we add them together, and then if we assume that they are independent, and then all together, it is quite obvious, but it will follow the chi-square distribution with the degree of freedom of 8, n equals to 8. right? Because we just added 8 different terms of standard Gaussian, right? Because x11 actually followed the normal distribution with the mean of mu1, which corresponds to the first group's mean. Right? Yeah, we just subtracted the proper mean or the corresponding mean value from different groups, and then we just take the square of it and then divide it by the common sigma value, because we assume that they all have a common variance value. And then if we add these terms for all of these 4 groups, and then no, we had a 3 group, right? So in this case, sorry, so we had a we are assuming that we have a 3 groups, right? So in this case, 4 of them, 4 of them, 4 of them, and then in total we will have the chi-square distribution with the degree of freedom of 12, right? Or in general, if we have an M group, and each of these M groups will have an N observations, and then simply it will follow the chi-square distribution with the degree of freedom of M times N, right? So far it's quite straightforward, right? Any questions so far? Okay, so let's see. Okay, and then we will do one more thing here, because we do not know mu1, mu2, mu3. Yeah, so these mu's are unknown parameters. So what we typically do is to replace this true parameter mu by our sample mean, right? So it's the sample mean of the first group, and this guy is the sample mean. This guy is replaced by the sample mean of the second group, and this guy will also be replaced by the second group, right? So in this case, yeah, so let's just think about this group first. So it originally had a chi-square distribution with the degree of freedom of 4, but if we replace this mu's, the true parameters, with our sample mean, and then what will be the resulting degree of freedom? I mean, just when considering only that the green part. So originally degree of freedom was 4, and then 4 less than 1, which is 3, right? Okay, and then in the second group, we did the same thing on by using their own mean. And in that case, what will be the, it will also have the degree of freedom of, the degree of freedom 1 less than the original value, right? So altogether, if we consider